methodology for rapid implementation of high-value products incorporating leading-edge technologies. He has experience in large-scale distributed systems, cryptography, embedded systems, database engine development, compiler design, digital TV, and machine learning and AI. He was a keynote speaker at the AGI 2019 conference for his work on commercial neurosymbolic systems. He has over 70 issued and pending patents. So it's a delight to welcome Hugo. Over to you for your talk.
Thank you very much for that intro, and thanks everyone for joining. I wanted to start out by also introducing a colleague of mine that's at Cisco that's been working on this approach to AI. That's I think you might find interesting because we do share a lot of belief that neurosymbolic is key. So Oz, did you want to introduce yourself a little bit and yeah, just maybe talk a little bit about OpenRs as well?
Yeah, sure. Hi, everyone. My name is Oz. I'm a data scientist working at Cisco. Hugo and I have been working on some cool projects, and I want to mention a little bit about my journey to AI. My journey started when I was an undergrad student and taking automata theory class, and I was fascinated by Turing machines and automata, etc., which caused me to be interested in linguistics and then cognitive science. And I received some graduate degrees from cognitive science. And later on, I pursued another graduate degree in computer science, and I went to Temple University in Pennsylvania, where I met my advisor, Pei Wang. He's got a system called NARS, non-axiomatic reasoning system. And we started to study and work together. And that's how I met Hugo, actually. Hugo and my advisor, Pei Wang, are friends. And we started to work on neurosymbolic integration, AI, some interesting projects.
So we'll talk a little bit more about that. I think that the Pei's work with the non-axiomatic reasoning system, it's a learning by reasoning system that has this AIKR assumption. I don't know if you've heard of the AIKR, which Pei coined, but I think a lot of others, professors and academics are using this idea, which is assumption of incomplete knowledge and resources, right? As opposed to the expert systems and symbolic reasoning systems of the 80s and 90s. That Pei's approach was, well, if you're always going to have limited resources, how does reasoning work in that environment? How do you learn by reasoning? And we've done a lot of interesting projects that we'll show you regarding that. We have Ali on the team. We both report into Romana. I don't know, Ali, if you want to introduce yourself and say just a little bit about your approach, to AI, or are you okay with that? Okay, we may.
Yeah, so, hi everyone. So Hugo, so I wasn't really prepared to do anything for today, but as Hugo mentioned, I'm also very interested in this domain, maybe a little bit different in terms of approach from what Hugo is doing, but in general, we are very interested in the domain of symbolic and neurosymbolic, and the way that to use learn semantics from data and do the reasoning based on those higher level top semantic information. I don't want to take more time here, and I let Hugo continue this.
Thanks a lot, and I hope that next time maybe we'll have a session, focusing on your research as well. So in essence, we're very fortunate to be at Cisco and to be able to work on state-of-the-art approaches to AI. A little bit about to expand on some relevant aspects of where I'm coming from. When you think about AI, I think that one of the fundamental items of importance would be the issue of knowledge representation, like an engineering description of knowledge, right? Not a philosophical description from the perspective of there's a lot of thought about what human knowledge is about, justified true belief and all of that. that was the beauty of starting out at this company, Metadata, in the 80s, where we developed the first semantic networks and ontologies before RDF and all of that, where we really studied Korsivsky, his thoughts on what is the nature of knowledge in the sense of knowledge that would be applicable, a definition of knowledge that would be applicable to everything from AI systems, human, knowledge, as well as animals and other learning systems, any type of learning system. And when you take that engineering view of knowledge, just like Korsivsky, I hope that I'm sure some of you must be very familiar, right? The map is not the territory, very famous guy, but he was looking at coming up with an understanding of natural intelligence systems, in the sense of maybe he lived through World War I and II, and he was trying to understand how is it that from an engineering perspective, a description of man that describes why it is that we have this amazing intelligence, amazing improvement in ability to abstract and to higher levels of symbolic reasoning, and yet we have higher levels of disastrous wars, and other societal issues that are happening. And so he came up with an engineering definition of, and that was the beginning of my foray into this. And we'll get into this in 1 second. We are gonna wrap up our part in 20 minutes or so that we can have more interactive discussions and questions, or we can keep talking. We can talk about this forever. But briefly, the Korsivsky's engineering definition of man, it started out with first of life, right? So he defined plants as chemical binders that, in essence, gather sunlight and or other sorts of energy and convert that into and bind that in some way, and store it. And animals as space binders, and his descriptions are trying to be engineering descriptive and predictive, not just like philosophical or spiritual. He didn't talk about those things. And so animals were space binders, and humans would have the unique capacity to be time binders, right? In the sense that, with our levels of abstraction, our ability to have our symbolic representations externalized in books and writings and in verbal, communications, and that was a unique thing. And then when he tried to go further, and that was Manhood of Humanity, where he really kind of dove into those descriptions. Then he said, well, what's the problem? Why is it that the ability to abstract, why is it that we're so prone to these major societal and human issues? And that was where he started to talk about, that we need to become aware of our abstracting processes, right? So we talked a lot about knowledge and how we learn and how we store knowledge and how we can have, in essence, humans have infinite levels of abstraction. And this power of abstraction, it turns into, it has some problems. If you're not aware of it, if you're not, cognizant of it, you get into, you mix levels of abstraction, and you come up with problems where you are dealing with your own abstractions as if they were real, right? And so abstractions and that leads to, the mixing of levels of abstraction was considered one of the serious things. But fortunately, all that work turned into some cool ideas about how AGI systems could learn and represent knowledge. So let me see if I could share something here in a minute. Yeah, so let me I'm going to share some slides. These are all, we have a few, if you look us up on researchgates.net, you'll see that we have a few papers. We'll kind of give an overview of those. I'm going to share a screen, screen 2. Okay. Let's see what happens here. This is a depiction of one of the beauties of working at Cisco is that we are applied. We get to have these theories, work with academics and professors, but then apply it to massive scale data. This is one of the recent works that we did in a neural symbolic system for self-supervised learning on massive time series sets. So we had 300,000 time series this is the K is for our code name Chronos, but that's internal. And that's just a, kind of a nice animation that we came up with. So the time series are coming in and insights are being automatically in a self-supervised way coming out. But let's talk a little bit about our neurosymbolic, first of all, this neurosymbolic approach based on a metamodel. And then we'll show some of the applications that we've developed using this. So going back to Korsivsky, what he noted, he did classify things, and we've actually kind of formalized it in our own way. We have L0, where that's raw data coming in. It could be symbol data, natural, it could be text data, it could be anything, or just time series, video data. L1 is where we map the subsymbolic data, in L0 to whatever prior knowledge you have. We begin to kind of add labels and link them up. So this other icon that you see here is a video product that we're working on. Again, these are just internal code names. It's not official Cisco product, just to be clear. So we start out with this metamodel, right? And so and our initial focus was to and all the abstraction occurs in this L2, right? And that's why you have levels within L2. The absolute levels are not that important or even necessarily known, but they're relative levels, to know if you're talking at the same level of abstraction or a different level of abstraction. We keep track of that. And so this is a very high level of understanding or representation of our of the metamodel that we have. And so within this context of this metamodel, there's a couple other key things that we've applied, which is the framework for learning systems. They have to have go beyond statistical learning. We do definitely leverage machine learning and deep learning, so those are integrated. We'll show you how we do that. We also have learning in the symbolic domain. So, for example, the non-axiomatic reasoning system, ERA, OpenCog, these cognitive frameworks are able to actually learn by reasoning in an unsupervised way. So we use both of those, and we integrate the knowledge into this metamodel, which we found to be kind of crucial, at least so far, for the applications. And we'll talk about why that is. The other aspect, briefly though, is that we have a clear way of identifying asymmetric relations, distinction that you would characterize as distinctions, like this is not that. That seems to be the basic, framework or the kind of the backbone of knowledge. And then you have similarity relations, symmetric relations that sit on top of that, connected with, and then so you have the symmetric, anti-symmetric, and these levels of abstractions. Again, we have references, you can see our papers on all this if you want to really dive into this. But and we have unsupervised learning in the symbolic and subsymbolic. It's really more self-supervised than the subsymbolic. We'll briefly touch on some of these. Yeah. Okay. The more recent paper that we have out there that we'll briefly discuss covers the role of attention, so system 1, system 2, attention, those kinds of thoughts, we do cover that as well. Attention, in our model can come from the subsymbolic space, and also from the symbolic space. They do have different speeds of operation typically, and most importantly, it has to do with the focus of control, right? Is there like a controlled thread? Is it single-threaded, operating primarily in the symbolic space, or is it multi-threaded, subsymbolic? We talk about that in our one of the papers here. And these are the papers that we'll discuss. So what I wanted to do was, before we get into the, maybe discussing these papers, I don't know, Oz, if you want to say anything about these. I wanted to talk about the smart city, application a little bit, since that was our first deploy. So we've actually deployed neurosymbolic systems into different environments and domains, and I want to kind of talk about that. But I don't know, Oz, if you have anything you want to chime in here.
I think the traffic application is a good example. One of the first applications commercialized using the neurosymbolic approach.
Well, I wouldn't say commercialized. I think that would be going too far, but it is. Let me see if I can make this a little bit bigger. I can't. There's a lot of things blocking the header here. So in this paper, and Oz was involved with this. He was just joining at this time. You know, this was our first attempt at getting a neurosymbolic system operational, and so you can read about this one. And this one leveraged the reasoning. It's called OpenNARS. It's an open source project that you can see out there. And the approach was to take machine learning and deep learning based processing of video to get the object detections from a YOLO, and then we fed that into a tracker that we implemented, Kalman filter and Hungarian algorithm to get the tracker going. And then we fed what we call tracklets. I think it's kind of a well-accepted term. Tracklets are for each object, it tells you, where it's been for X number of frames. And so you get these tracklets, and then we fed those into our reasoner, and that was kind of our initial neurosymbolic system without any metamodel, without any shared, it was just, a sub-symbolic processing of the video, tracklets feeding into OpenNARS, and we found that it worked fairly well. I mean, it was impressive in the ability to learn by reasoning, and we were able to define a few high-level rules for OpenNARS that would say, things like related to traffic safety. So what we did is we were able to say in the traffic safety domain, here's a high-level rule that says if you have any two objects that are moving, and either there's contact between those objects in traffic, that's pedestrians, bicycles, any kind of vehicle that's moving, whatever that is. And they make contact, or they're predicted to make contact, they may be a safety issue, right? Either one of those. And so with that very high level rule, we deployed it, and it was able to find a lot of, very subtle, traffic issues in real time. And so we had pretty good results with that. The one thing that we did have to do is the system also was autonomously learning its environment. So it would observe the motions of the different classes of objects, and it would create a grid world, quantized space, that would identify sidewalks, roads, the key features, crosswalks, and that sort of thing by not just the visual cues, but the behavioral cues. Overall, I would say it was a success. But then that took us to the next paper that we'll discuss here, which was we then tried to apply the same technology to see if we could revolutionize retail inventory, right? And that led to this paper. I don't know, Oz, if you want to talk about when we first tried to just apply that same architecture of the smart city into different retail space.
Yeah, retail, different domains. We tested in retail and also some applications with computer networking, and we observed amazing results. Especially.
No. Initially, though, I mean, when we had the same architecture as a smart city. If you recall, what happened was, so again, there was no metamodel there.
We had combinatorial explosion issue, first of all, and we also observed that the knowledge we acquire kind of scrambled. So we got a soup of knowledge, which caused us to work more on metamodel generation and create a more structured knowledge representation.
Right, and so the first problem was, like I said, the combinatorial explosion that you see, even though NARS had the assumption of incomplete knowledge and resources, when you got into, it turns out that we had many more objects, that we were dealing with in retail spaces than we were in traffic, because we were using YOLO we were getting a lot of thousands of bounding boxes in these scenes, because we were dealing with confidence levels that were quite low. So a lot of these things were just incorrect, bounding boxes to reason on. And so the combinatorial explosion issue that you get with most, expert systems that NARS is really good to, it does a better job in general, became a problem. And so I always had the Metamodel ready to go. And so we said, hey, let's try the Metamodel and see, if it can, with the abstraction, can we use abstraction to be a natural partitioning of the problem space, so that we can still reason with it, but we would reason in the domain of more of a linear, where NARS was not having these exponential, explosion issues, combinatorial explosion issues. And it worked amazingly well, right? So we started out with a scene from Starbucks, and can the system just, you point a camera, it learns where the shelves are, it learns where the products are, autonomously. And the accuracy in this kind of environment was 100%, which was very strange for us, right? Because you never get anything that's 100%. And then, we had some basic spatial semantics that we added to the system, but it was an indication that the Metamodel, at least as a partitioning scheme, and that we use it as a focus of attention, right, Oz?
Yep, exactly. We represented this image with the shelves and products. We converted that world into a world of bounding boxes, and then used the reasoner NARS basically to reason on it. But when you have a couple hundred products and dozens of shelves, the binary relations among them, you end up with thousands of relations, and which cause the most of reasoners not to function properly.
So that was considered a success, and we applied that to some networking problems, which then took us to the next level of issue that we discussed a little bit in this paper, but also, if you look at ResearchGate, our recent Frontiers in Psychology paper gets into the role of attention. Let me see if I can bring that one up for a second. But the primary issue when we went to networking was that the systems that we've discussed so far, you'll notice, didn't have self-supervised learning, right? They required a human expert could write a couple of rules, like the rule of any objects that are moving that might make contact, could be a safety issue, or so humans had to do that. In networking, we found that when you're dealing with hundreds of thousands or millions of time series, you couldn't get away without self-supervised learning, right? And we talk a little bit about how that works here, but that is something that we've managed to incorporate into this. And so what we're seeing right now with this, if we go back to our architecture. So now the more recent development that we had was self-supervised learning in this domain. We are still, we have a lot of patents in this space, so we should be able to, with Cisco's blessing, publish something, hopefully, that talks a little bit about our approach. So far, I think we have been able to talk a little bit about it in some of the papers, but when you now we were seeing that this is, you have a model of knowledge, unsupervised learning and self-supervised learning in the symbolic space and the sub-symbolic space. Now we've also looked at natural language processing. We feel that we're getting, and the different applications that we've applied this to. At a very high level, I could say that and this is hopefully this is just an introductory discussion for all of us. That we could talk more about these. We have all these links here. If you want to kind of double click on this. But at a high level, I think this is what I want to just kind of start the discussion with, was to give you an idea of what we're doing, why we're doing it, some of the applications that we've applied. And maybe if there's any questions at this point, otherwise we can talk about a few other things on our side.
I have a question. I'm confused about what the problem is that you're trying to solve. Like, what's the input? What's the desired output? And I also don't know what the word neurosymbolic means.
Oh, okay. That's good. That's good. So the problem that we're trying to solve is to come up with more intelligent systems. More generally intelligent systems that can. One key thing that we want to do is cumulative learning, right? So why is it that with ML, machine learning and deep learning systems exclusively, when you don't have the neurosymbolic aspect to them, why is it that when they're, they can't continue to learn over time, right? You would expect that, if you had an intelligent system and it was, say, a video camera system, that it would get smarter over time. And instead, what you see is catastrophic forgetting. It doesn't really, so cumulative learning, more ability to generalize well, right? Why is it that when you teach, when you want to create a system today, like an intelligent AI system, why is it that it requires hundreds of thousands or millions of examples, whereas a 3-year-old, basically you just say, okay, that's a car, and then you're done. Right? So we would like to get to that level of rapid intelligence, rapid learning, right? And our system is doing that now.
Could you describe a bit more concretely what your approach is to meet that goal?
The cumulative learning, or both of those, the ability to learn more quickly. Let me just address the key issue of first of all, the cumulative learning is because we have this knowledge model, and if you want to have a system that continues to learn, it means what we found is that you have to keep the structure of knowledge, straight, distinct, the symmetric, anti-symmetric, the abstractions. Otherwise, as Oz points out, if you're just learning all sorts of statistical information, this happens 30% of the time, that happens 20% of the time, and you just keep aggregating all these statistics, it's hard to reason or use that knowledge. It becomes a soup of knowledge. So that's why we went to this this knowledge model that we have. Regarding the ability to learn much more quickly, specifically, so our system, the way that, as you know, machine learning and deep learning work today, you have to come up with large training sets, typically labeled, but you can also do a lot of unsupervised learning, and you get, you build a statistical model. What our system does is you don't have to have this pre-trained, this ground truth to start out. So if you just present it with a lot of data, the system, like a 3-year-old, observes, and builds this model of knowledge based, and applies it to what it's seeing. For example, in human behavior, right? What the system would do, it would say, oh, okay, so there's, people do this, and they seem to sometimes, move in this way. We would know it's walking, but it wouldn't have any labels, because it's learning all of this, just like say a 3-year-old doesn't know any labels. It's watching traffic or whatever it is. It learns these common, sorts of behaviors, temporally correlated things, spatially correlated things, and it classifies them and it puts them into this knowledge model. And so that then the training becomes, you can ask the system and say, okay, well, what are the 10 most important or most common behaviors that you've seen, or most extreme behaviors that you've seen? The system could provide a couple of examples, and you say, okay, oh, that's walking, that's running, that's a traffic accident, whatever that is, and you can apply the labels in a more, what's called more of an active learning approach. So neurosymbolic is just about, going back to that question, it's just where you combine what's often called subsymbolic processing, which is machine learning, deep learning, dealing with, ones and zeros, with and so that's the current brand of AI that's in kind of vogue for the last 10 years or so, since the advent of new compute architectures like GPUs and all of that. And then the symbolic AI is more where AI started, with Minsky and McCarthy and a bunch of other guys that, much of, maybe back in the 60s, and they were looking more at, language and cognitive function, cognitive neuropsychology. That's more recent. So how does, from a higher level perspective, how does, the psychology aspects and all of that would be considered more symbolic, or more in the symbolic space. And neurosymbolic, I think that what a lot of us are interested in is how do you come up with systems that have both the symbolic and sub-symbolic, aspects to them, which I think that in AI today, there is a strong belief that the two are important, that we need to move, to neurosymbolic architectures. I see that because we've over-rotated as an industry and in academia with the sub-symbolic, MLDL is a big thing. What tends to happen is the focus is on taking symbolic knowledge, like say human knowledge that's in an ontology, and then converting that into a statistical model to be processed by MLDL, which is not which is fine. We also, my focus has been more the other way, right? Which is how do you get sub-symbolic information, put that into symbolic representations that you can then, do these new kinds of reasoners, OpenCog, OpenNARS and ERA or whatever. So those are a couple things that we've done. But I probably haven't answered your question. I think there might be longer discussion topics, but thank you very much for that.
That helps a lot. Thanks.
I mean, we had some slides that we came up with a storybook actually, to just kind of introduce what this stuff is, So if there's please chime in if you have other questions. But just briefly, we came up with this to try to just highlight, this is your convolutional neural net, which is amazing, right? In the sense that it builds a hierarchical model on its own, and that's what Jan LeCun and a lot of us were very excited about, right? That it breaks things up into levels of abstraction on its own, really, and that kind of map the way that animals and humans, the visual cortex works, right? So edges and color patches and textures and different shapes, and then finally object classes. The famous case of Andrew Wynn, detecting a cat with his Google Brain, right? It kind of was an interesting thing there. So yeah, that's great. The thing that we noticed, and one way to understand the problem is kind of seen here, which is when you look at how a deep learning model determines the class, right? It's that last layer, that says, okay, so now you have this model here, but now you're going to have a statistical model that says, is it a panda or is it not a panda? The issue is that, the information that the deep learning classifiers typically use. Here we're saying this is a saliency map. So I don't know if you can see these like light yellow and green areas. I don't know what color it shows up on your screen, but so these show what the areas and the patches that are being used to make the determination by the deep learning system that this is a panda. So it's mostly around this big black eye area here, and the ears, and something about the nose. For wolves, it's like so. And of course, we're getting better. The adversarial learning, this is kind of maybe a little bit out of date. We wrote this a couple of years ago, but still, it still does highlight that the classifier at the end of the day is not using, like a child would say, well, it's the panda is a fuzzy animal, and it lives in a zoo, and they use all that sort of information, and that's kind of one of the ways that we highlight why maybe neurosymbolic is a good idea, right? That you don't want to make classifications just based on this, because you can easily, you can change a few pixels, and a human would still say that's obviously a panda, but if you change the right pixels, you could change a traffic sign into a different traffic sign, right? Stop to go. So yeah, so here we just talk a little bit about the combination. So this is more of a general neurosymbolic kind of thing. And then here we talk about the importance of the knowledge representation, and it turns out that Korsivsky argued that even in single cells, learn, And I think there's evidence that they do, right? They can tell the difference, you know, if they behave differently with predators and food. How does that work? And the model of knowledge that we're building, the engineering, you know, and if you go back to Korsivsky, it actually does cover learning in single cell. It actually covers learning in what he called electrocolloidals, you know, which is kind of in the cytoplasm, that you get these channels that on the membrane of the amoeba. The channels, you know, are kind of how it senses and learns, you know. So anyways, are there any other questions while we go through this, or?
Hugo, could you maybe go back a couple of slides? You were talking about, you had this AI 2.0. Could you maybe explain a little bit more what's going on here in the slide?
Yeah, actually, this is a good chance for us to jump in. You actually created this slide. You want to get into it?
Yes, so that was an example for maybe an adversarial attack. We have a panda image, and when we add some noise to it, we can fool the deep learning model or play with the confidence value of the classification. What we do is we integrate symbolic knowledge with a statistical model, which provides another channel of knowledge. For example, we see here we have a mammal which has a face and color, eye, snout, etc. We can identify the pieces of an image, and then create a symbolic knowledge around those pieces that we are detected, so which gives us a power to be resistant against noise and adversarial attacks, etc.
So are you saying you would have multiple classifiers? So you'd be having a face classifier, eye classifier, snout, tree, all these kind of classifiers.
Location.
A location, etc. And you would then use these somehow also to make classification rather than the image itself directly.
Mm-hmm.
Yeah. So here you're go ahead, Hans. Sorry, I don't want to interrupt.
Yes. Yeah. I was just saying yes. Exactly. Mm-hmm.
More in the symbolic space, right? So now you're using the neurosymbolic system and what you know to improve adversary attacks.
Another way to do that would be to say, basically you're just kind of extracting features, right, which maybe make semantic sense to a human, like eyes, color, etc. And then you're just fitting. Well, I guess there's many ways to do that, but one way to do it would then to say, well, for each image you have a corresponding discrete vector of attributes, right? For this particular case, the face is positive, it's white, it's got eyes, etc. And then for the class of, say, pandas, you just fit a distribution to those vectors of attributes, right? And for other animals. So I don't really know why. I mean, do you need the graph, or
So now you're getting into the as you know that causal models cannot be represented in statistical models, right? So what ends up happening is if at the first level you get something that says, okay, there's a 20% chance that in this vector that this is an eye. There's a 50% chance that's a nose. That could be a ball, or it could be an ear, and then you try to build a hierarchical statistical model from that. You have a very complex set of statistical probabilities that do not equate to a more causal model saying that, okay, I know I'm in the zoo, and so the causal reasoning is a way to kind of short circuit a lot of that. Now, do you get the problem of stereotypes, where now you begin to use your abstraction to process things that your stereotypes could be wrong at times, right? So then you need to kind of go back and look at the details of what you're seeing there. So we're finding that one of the key limitations of the vectorized probabilistic models is that there is just no way that you can do efficient causality modeling and so if you look at Judea Pearl's work, and I think there's a lot of better explanations as to why you need to move beyond just statistical models. We found that just empirically that if you don't move into more of a metamodel approach that has distinctions and symmetric, anti-symmetric relations and abstraction, the system got lost very quickly. So we needed to simplify, by having this higher level, symbolic model. But I think, there's definitely, a lot more that can be done on both sides. So we're not, just to be clear, we're big proponents of, MLDL. We were like one of the first, actually, probably the first to have any kind of deep learning video analytics 10 years ago out there, back when everything was, so we're big fans of MLDL. It's just, we also see that there's value in the symbolic reasoning and neurosymbolic architectures.
Just a question, like, are this symbolic part here, is it learned or is it encoded? Do you have like a knowledge base or things like that? So for instance,
so with us, it's always typically not going to be an either or, right? So initially this was entirely coming from ontological data. We integrated with the biggest, like if you're familiar with Yago, which incorporates WordNet, ConceptNet, all the big ontologies and all of that. So we started out with that approach, but in the new self-supervised learning that we're developing, that we developed actually, is working for the sub-symbolic space. We have a lot of nodes and tags that are just learned internally by the system, and then we try to apply, kind of link those things that we've learned with labels that make sense to humans, but we don't always have those links, to humans, and it's not always possible, right? As you self-supervise, when you learn the behaviors of traffic and behaviors of people and all this kind of stuff, it learns a lot of things where there's just not in English, there's just not words for them, right? It's just but it's still an important concept. So yeah, we started out primarily with leveraging the biggest ontologies out there, Yago specifically, and there's a big project out there too that's great for neurosymbolic. If you're looking at Yago and also the Ambiverse, where they're doing sort of more advanced semantic language, NLU, natural language understanding. It's over at the Max Planck Institute. It's an open source project.
Yeah, thank you.
Thank you. These are great questions. Any other thoughts? How does this? Are there some neurosymbolic researchers out there?
Yeah, it'd be nice to have a sense of, I see that maybe imposing some kind of hierarchy could be useful. That's a good way to encode, human understanding, or the way that we think about, say, a panda. It'd be great to get some data on that, though, like, actually, that this does outperform, just say, some standard statistical model, like, just take these attributes which you learned from the image, and just fit basically a classifier to those learned attributes, and see if that can actually outperform or rather the other way around, say, the hierarchical model that you have outperforms, say, just some standard, classifier on these extracted features.
Well, what about all the thing is that if you just go with what you can extract from the image itself, I guess you'd have to have, if you could also incorporate, the temporal aspects, the contextual aspects of, is it in a zoo, all these other things. Yeah, I guess, that could be a good way to kind of compare and contrast the two. Yeah. Definitely a need to incorporate much more of the contextual cues as well. That might be difficult to get directly from features of the image, but it's worth a try.
But as I understand it, though, I mean, the way that you classify the panda, right? I mean, I don't know exactly if this is what's going on here, but I would assume that you're running a set of feature extractors. Is there an eye present? Is there a branch in the tree present, etc. You can have this collection of attributes which are associated with this particular image. Those attributes, they may have probabilistic values associated with them, but those are then fed into some hierarchy or some however you want to encode that, which then comes up with a description as to whether or not this is actually a panda, right? That's how similar your thing is working. It's a two-stage process, right? It's a feature extraction process first, and then you basically see how that those features are extracted. Does it have a snout? Yes, no. How that actually fits with your reasoning model, your metamodel, as you call it.
Yeah. So yeah, that could definitely also work. Might be a lot of additional computation versus when you have say a high-level rule that you can just apply. But I think with the ability to do both, could be very interesting. And you should be able to select, which mode is more interesting. Like when you look at Piaget and human development, how humans tend to be extremely abstract, right? Toddlers, yeah. So they work more like this, but then if you become an artist, you go back and you just process the raw pixels again, so you can actually see. So you have to learn how to see, right?
So I guess what I'm asking is, like, let's imagine I gave you a picture of a panda, right, or your system. I say, here's a picture of a panda. What does your system do? What are the stages of processing that it does? So I'm assuming, from what you've been saying, that
this is an example. I think this is a bad example in that sense. It was kind of our we don't really there's not a big need to look at pictures of pandas. So most of what we do is more, we have to get into the temporal domain, to say, you want to really understand temporal behaviors of things, and learn that autonomously and all that sort of thing. The panda example is just something that gets you to, at least understand conceptually how a system that can reason, neurosymbolic system can be more resistant to adversarial attacks conceptually, right? But if you really want to break this example, I think it's like, why are you processing pandas this way? But, which we don't. We wouldn't use it this way.
Yeah, I guess other people might call things differently. I'm still struggling a little bit to understand what's going on in general, but I think what you're saying, maybe this is a poor example of it, but is that when you're talking about neurosymbolic reasoning, I think what you're saying, although I might be wrong, is that you're actually doing an initial step which converts the, whatever the input is, into some symbolic representation. So for example, this may be a bad example, but in your case, with the panda, you have a symbolic then representation as to whether or not this input contains the presence or absence of certain features, like is it got a face, what color is it, etc. And then you're in symbolic form, and then you can use your symbolic reasoning after having done that initial step. So the initial step would be your neuropod, right? That's what you might think of as your the neural part of your so-called neuro-symbolic reasoning. Is that correct?
That's correct. The only thing is, I think that what we found is that when you're trying to understand the lower level features of systems, that in general they are what's the fundamental unit of representation, right? And what we're seeing is that at the lowest level, it's something like a time series, but more of a data series, right? It's a series of, so temporally, when you look at any sensory channel, it's obviously a time series, right? What may be less obvious is that even understanding the shapes of an image, those shapes can all be converted into data series, right? So you can get the centroid of the shape, and then you can, convert any shape into a data series. And so we're seeing that fundamentally everything kind of converted into data series now gives you a fundamental language to represent all data that you can then correlate. You can then apply some of the new techniques that we're looking at to turn that into symbolic representations. And we're seeing that temporal evolution is kind of when you think about how do you self-label, how do you do self-labeling or of things, the temporal modality gives you kind of a hypothesis or an initial basis for assuming that there's some sort of a causal link between temporal frame, temporally adjacent, things that occur, right? So that's a self-labeling. The other one is multi-modalities, right? So if you have like multiple sensory channels, the correlations among them could be seen as a potential self-labeling as well. But I think you got it basically. That we do look at the raw data, convert that into symbolic information. We're trying to do more in the symbolic space, which I know there's going to be a lot of resistance, because I think the push right now is the other way, right? Is to do more processing in the statistical space. I think both are important.
Great, thank you.
Thanks a lot.
Hi, can I make a more specific question about this interaction between the neural layers and the symbolic layers? So going back a little bit to the retail example, where we had the shelves and the products. And so as far as I could understand, in a way, like this sub-symbolic part would be learning the bounding box of the objects, and then perhaps classifying if the bounding box a product or part of the shelf. And then that can be fed into to make a knowledge graph, right? Oh, this product is on the left of this one, is inside the shelf. My question is, what is this like? How is this process done from going from the classified bounding boxes to the actual knowledge graph of the relationship between them? Is it more of a
that's really a very key question for the retail, and thank you for asking that. So the first thing we should clarify is that if we required having a classifier for the bounding boxes of the objects, that we found that would not work as a system that you could just point and click and say, okay, go do retail inventory in an autonomous fashion, because the system doesn't know upfront what the products are. You don't have models of anything, right? So you don't know what the products are. You don't know, so that would take you back to our incentive from a commercial aspect was to be able to just point a camera where there's some inventory and shelves, and it just learns everything on its own. So what we started with was actually we tried this and it surprisingly worked. Where we said, what if we just take the YOLO model, which does give you the classifications of objects, right? But now it doesn't know what the objects are here, up front. So what we said is, we're going to look at all the bounding boxes when YOLO has like 0 confidence, and that's where it came up with thousands of potential boxes, right? So now you have this set of thousands of boxes. Most of them are completely incorrect. Confidence is very low. And we reasoned on that space, right? And what we did is we came up with the idea of spatial semantics, right? And said, okay, well, we know something about what shelves are, how they line up, and we had something that identified shelves. Then once we had shelves, we said, well, let's just use spatial semantics to say things that are these boxes that are like really aligned with, seem to be located on shelves, maybe a bounding box of interest, right? And so and the containment, so the spatial semantics plus these random, bounding boxes that we have, were able to get us to 100% accuracy on the cases where we tried it. And we try to break it, right? To say, well, we because we don't like 100%, we want to understand where it's breaking, and so we said, well, let's put it where there's no. Let's try this on images of inventory where there's no shelves, for example. But the system was looking for spatial semantics for shelves, and we've like hanging products and things like that. And we found that it worked extremely well, even in those cases. It was generalizing, and the spatial semantics seemed to work. But yeah, the idea, that would. In general, I think that one of the things that we love about the neurosymbolic approach to this is that we can go back to raw pixels, and if things are moving, even if you don't have a classifier for the thing that's moving, if the deep learning system just doesn't see it at all, right? Because it's not a known object, we still see it, right? So there's kind of this deep learning blindness, right? If you have to classify everything up front, you miss a lot, we find. So, but that was a great question, but I think we're out of time.
Okay, thank you.
Thanks a lot. So I think that's it then, right? Thank you very much, everyone.
Thanks for having us.
Thanks, everybody. Anybody has any questions? I don't see anybody asking anything yet. But thank you, Hugo. Thank you, Oskin. That was really fantastic. It was great having you. And I think we will organize another one shortly.
We would love to join and be part of this this group. Thank you very much, everyone, for your time. We really appreciate it.
Thank you. Bye.